All right, so here we are in our new classroom. That's pretty dark. I guess this will have to do. All right, let's take a look at what's next. Homework 2B is going to be due a week from today. This assignment maybe takes a little bit more time, but you can get an early start on it because we've already covered the concepts, for example, that you need for problem 29. Let me just emphasize, on problem 71, I think that's the kind of thing where it's a yes-no question. But if you just said yes or no without any supporting rationale or like details or calculations, then you wouldn't get any credit. So I know the way it's phrased, it's a yes-no, but go above and beyond for that one. Just go ahead and explain your answer. All right, today we're talking about pressure and surface tension. So any questions just in general before we get started on the new material? Did everybody have a good weekend? Too short, right? All right. So anybody know what this is? It seems like every semester I have some classic car lovers in the class. I don't know what it is. You think after so many semesters I'd figure out what car this is. Did you say it's a Charger? Is it a Charger? Okay. Well, it looks pretty shiny, but we're not talking about the shine today. Let me dim the lights just so you can fully appreciate it. All right, there it is. Nice looking car. All right. The reason I show you this is we're going to talk about the tires. Maybe it's the least exciting thing on the whole car is the tires, right? But for today, that's our most exciting thing, is the tires. Now, the pressure in the tires is normally, if you use a gauge, like if you connect, you see how there's a little gauge here. Sometimes they have just a stick you put on there and the stick pops out and it tells you the pressure in the tires. When you measure the pressure in the tires, if it said 0, what that would be doing is it would be telling you the pressure of the tire relative to the Earth's atmosphere. It wouldn't be saying the pressure of the tire relative to the vacuum of space. Those would be two different measurements. Anybody in here see that movie Gravity? Sandra Bullock, I think George Clooney. All right. So in that movie, you sort of get a sense for the vacuum of space. Like it's silent there. You can't breathe in the vacuum of space and so on. So we're just going to be talking about the pressure of gases. Now, if we were going to suck out all of the air from this tank, then this gauge, which normally says 0 is the atmosphere, would actually be reading a negative pressure. And so one of the confusing things that sometimes tricks students up a little bit is what reference system we're going to be using as the basis for measuring pressure. There's two main ways of doing it. There's what we call the absolute pressure, which is where we're using the vacuum of space as our starting point, meaning there's no gas molecules in a perfect vacuum. In a perfect vacuum, this would just be empty space. There's no nitrogen in there, there's no oxygen in there, nothing. So that's a perfect vacuum, and that's what we'd say is 0 absolute. But in the gauge pressure, that's the second kind. Gauge pressure is when we're measuring pressures above and beyond the Earth's pressure. And so we're using just what we normally think of, well, there's no pressure in this room. It's just normal. Well, normal is 1 atmosphere for us, or 101.325 kilopascals. You'll learn over time the different definitions of 1 atmosphere. Okay, so here's the written definition of what we've just talked about. Absolute pressure is where you're starting with 0 gases, or a perfect vacuum, as the measuring point. So, I'm sorry, you can't come in after the class has already started. The video will be posted online. All right, so in Huntington, which is where I usually live, or here in Sharjah, absolute pressure is 101 kPa. That's the typical sea level pressure of the atmosphere. Now, of course, that varies from day to day. You know, because of weather patterns, sometimes the pressure is a little bit higher, sometimes the pressure is a little bit lower. But this is the average atmospheric pressure at or near sea level. In my tires in the car, I have this starting point, I have 1 atmosphere, and then I put in some more pressure as well. And that's why I'm able to drive on the tires. They can support a load of the vehicle, is because they have additional tires in the pressure. That's what keeps them rigid, and so they don't just deflate and deform. So you can notice that ABS is the subscript there. It means the absolute pressure. So if we're measuring those pressures relative to the vacuum of space. Now gauge pressure, of course, is a little different. That's where we're saying, let's ignore this. Let's just cancel it out of our measurements entirely and just measure everything with atmospheric as the starting point and then go above that. And so the gauge pressure of the atmosphere at sea level is 0 kPa. And then my tires would just be measuring how much extra pressure is there in my tires beyond the atmospheric. So that would be 234 kPa. 2 basis points. Any questions so far on how we measure pressure? I've got a graphical representation in a minute that I hope will clarify it a little bit more. All right, so we're thinking of the vertical axis here. We're measuring pressure. There's no meaning to the horizontal axis here. We're just saying we're measuring pressure above some starting point. And so vacuum is the absolute starting point. You'll notice that there's a hard line here because there's no such thing as getting pressure below 0 absolute. 0 absolute pressure is the lowest it can go. When we go 101 kPa above that, that's Earth's atmospheric pressure. Now that's not the same atmospheric pressure everywhere on the Earth. If we go to the top of a mountain, then the pressure will be lower, right? And if we go to a different planet, the pressure would be different there as well. Some planets are lower, some planets are higher. But for us, 101 kPa is our atmospheric. So let's look at where my tires are. If we measure from the vacuum line, this long arrow here is 335 kPa. So that's the distance from the absolute 0 to my tires. If I'm measuring it in terms of the gauge pressure, that line is shorter because I'm just starting how far above the atmosphere is the pressure of my tires. All right. By the way, this isn't my car. So when I'm talking about my tires, I wish I had something this nice, but I don't. So I don't think that matters. All right, let's think about the gas law. Last time in class, we talked about how PV equals nRT can be rearranged, and so that for any gas, we can find the density of the gas as the function of its current pressure, the temperature in Kelvin, and the R value that's specific to that gas, which we can look up in the back of the book as a fluid property. By the way, I mentioned that T should be in Kelvin. If I hadn't reminded you of that, is there anything on this page that would give you a clue that you have to change your given temperature into Kelvin? Exactly. Yeah, if you're looking at this R value, that's telling you, oh, here's the key. Our density will be in kilograms, the temperature should be in Kelvin, and then this joule, we could break it apart into its base units, and that's where we're going to get, ultimately, when everything's combined, we know density is kilograms per cubic meter. All right, so what I'd like you to just take a crack at really quickly is, for a tank of oxygen that's 2.5 cubic meters, that's the volume of oxygen inside of this tank. The pressure is 7650 kPa, and that's the absolute pressure, which is when we're working gas laws, we'll be working in absolute pressure. And then the mass of the tank itself, just the steel of the tank, is 50 kilograms, and the temperature of the gas is 120 Celsius. What's the total weight, meaning the steel of the tank and the gas? And by the way, how do we measure weight? What units? Newtons. Right, so mass is kilograms, newtons is weight. All right, so go ahead and collaborate. I'm glad we have these desks now. It makes it easier to talk to each other. So let's see if you can find out the total weight of the gas once you find the density of the gas as your first step. Okay, so what are some of the tricks of this question? You know, there's no such thing as a trick question, really. But there are tricks in each question sometimes. like the main places students can easily stumble is on the pressure thing. You know, and remember earlier in the semester I said I'm always going to write the units on every step when I'm doing my examples for you. So I'm never just going to write the numbers themselves. I'm going to write the numbers, and then I'm going to write the units associated with those numbers, just to sort of show you that it's a good habit to be in, and it will save you time, because even though it takes a little bit longer to write those numbers, you're going to make fewer mistakes, and so overall you'll save time. So once you find the density, then you can find the mass of the oxygen. So the volume of the container by the density gives you the mass of the oxygen. I found the total mass and then convert it to weight. So any questions about this one? All right. All right, I've got a video clip to show you now. Video clip 5. Let me dim the lights. This is a cup of water. It's a razor blade, which is made out of steel, and it's floating on the water. So the only explanation for this is that steel is less dense than water, right? Is that true, though? Steel is pretty heavy. Let's watch what happens. So it's floating there on the surface. It gets poked with the pen, and then it sinks. Let's watch that again from the beginning. Okay. Now you'll notice that whoever's laying that razor blade down on the water was pretty careful the way that they put it. They didn't just throw it in. They didn't lay it down sideways. Why do you think that they so deliberately placed it? Let's watch that again. You can see that they sort of hesitate as they're starting to lay that razor blade down onto the water. Watch for the pause. Very carefully. All right. Why the pause? Why is that person being so careful about it?
So water doesn't go through the empty spaces.
Okay, so water doesn't go through the empty spaces. What were you going to say?
Surface tension.
Surface tension? Okay, what do you mean? You're definitely right, but what is surface tension? What's happening here?
Well, I mean, because of the water molecules, they're close together at the surface, so basically it will float because the two flat surfaces will be.
There's a special force at the surface of the water. What would have happened if this person tried the same trick but dropped the razor blade this way, so that this way touched the water first instead of the flat surface? We'll just slice right through whatever it is that's supporting this. It's like there's a special invisible layer. It's something we can't see, but it's almost like the same effect as if there was a plastic film over the top. It's like a membrane of sorts. And so that when this person is poking on one edge, they're pushing through that surface tension, and then the razor blade sinks. All right, so that, what's happening, we saw steel on top of water. And it's not because of the density. Actually, steel has a much higher density than water, and so if we're just looking at the densities, it shouldn't float on top. But it is possible because of the attraction water has to itself. And that's what's happening, is that water is a polar molecule, and so that water molecules are attracted to each other, and at the surface there's a little bit of leftover attraction because it can't reach out to water molecules above it. All that's above the water at the surface is air. And so it has like an extra strong attraction to the water molecules on either side of it. The same thing allows these little water bugs to float on top of the water. It's not that these bugs are less dense than water. They have a higher density, and so if it wasn't for surface tension, they just sink through. But this bug is spreading out its weight. You can almost sort of see the water bending in the vicinity of the legs. And so it's taking advantage of surface tension. The bug is walking on water. It's possible for a few reasons. If we look at the specifics, partly it's because it doesn't weigh very much. If this bug was heavier, it would go through the water. I couldn't do this, right? Even though I have pretty big feet, I couldn't step on top of the water like this. Partly because I couldn't spread out my weight well enough. My ratio of weight to how much I can distribute it is all wrong for walking on top of the water. For this bug, it's light and it spreads out its weight a lot. So what we can say specifically, maybe the most technical answer here, is that its downward forces, the weight of the bug, is less than the effects of surface tension that supports it. We can do a force balance and look at how heavy that bug could be and still walk on the water. So here's another example of steel in the top surface of water. You can do it with a razor blade. You can do it with a paper clip. And like I mentioned before, it's because of the polar nature of water molecules. So let's look at this more specifically. I mentioned that it's the molecules at the top that are causing this surface tension effect. It's because, think about a water molecule that's down below the surface. It's attracted to other water molecules, but it can spread out that attraction over the ones that are on either side, on front, back, below, above. And so the bond between one water molecule and any other water molecule is kind of spread out. But at the top, there's nothing above those water molecules for it to express its bond with. And so the bond it has with the molecules on either side, front and back, is relatively larger than the ones that are below the surface. And so these molecules at the surface are more tightly bound together than the ones beneath the surface. Does that make sense? Any questions about this? Surface tension is a fluid property that varies as a function of what is the liquid. It varies as a function of temperature. So if you look at water at 0 Celsius, you'll notice that the surface tension constant is higher than hot water. So as you heat the water, the bond that those molecules have with other water molecules is going to decrease. And if we compare water to mercury, for example, mercury has a very high surface tension. It's extremely attracted to other mercury molecules. And if you've ever broken a mercury thermometer, or you've seen or hopefully not handled mercury because it's toxic, but mercury sort of globs together. I mean, it forms a big bubble. If you put it on the table, it forms sort of like a mound of mercury. It doesn't spread out in the same way that water would. And even lower than water, for example, if you look at ethyl alcohol, it has a very low surface tension. So that's because the alcohol molecules are less polar than water molecules are. It's all about the shape of the molecule and then the individual atoms and their attraction for electrons. So we call this a membrane effect. And surface tension constant, sigma, is relating the force per unit length. And we'll talk about what that length is, but in the case of the bugs, it's the length of its legs. And there's actually two sides to the leg. We'd actually, if we're counting out the total length that it's spreading its weight over, there would be this length on the left, this length on the right, this one, so we would double the length of the legs because it's deflecting in two spots. If I do a little drawing on the board here, here's a cross-section of the bug's leg, right? This is the inside of its leg. And here's the liquid that it's bending down. It bends it here, and it bends it there. And so it's effectively doubling the length that it's spreading out its weight over. Here's the equation that tells us how much force the water is pushing up with when it's deflected. When the membrane is disturbed, how much the liquid can resist the downward weight. And so it's this surface tension constant sigma multiplied by whatever length we're spreading the weight out over. And so if you spread your weight out over a really long length, then the force is going to be high. And we can tell from this equation, if you want a big surface tension force, if you want to be able to support a really heavy object, then you have to have a long length. A big L gives you a big F sub S. So this is a really interesting effect. And it causes, it's not just limited to bugs walking on water or razor blades floating on top of water. It's also related to what's known as the capillary effect. And this capillary effect is something we can observe in the lab using small glass tubes, but it's also something that's very important in nature as well. In groundwater, which is aquifers under the Earth's surface where sometimes wells are dug to pump water out, a really important drinking water source or source of water for irrigation, the soil acts in the same way as these glass tubes. We'll talk more about the soil and how it behaves, but let's start with this sort of more pure example of the glass tubes. So if we took a glass tube and we stick it in the water, what happens is the water will naturally be sucked up some distance delta H. And it's not because there's a vacuum at the top of this glass tube. You'll notice this glass tube is open to the atmosphere. So the air pressure above this liquid surface is the same as the air pressure above this liquid surface. So of course if you suck on a straw it's going to draw a liquid up. But that's not what's happening here. Here the liquid is drawn up inside of the tube because the water is attracted to the glass in this tube. In the same way that water is attracted to other water molecules, water is also attracted to the silicon dioxide in a glass tube. Silicon dioxide, SiO2, is also a polar molecule, so that what's happening is the water wants to maximize its contact with the glass surface here. And so surface tension draws the water up inside of the tube. Now let's look at some of the dimensions that are shown on this drawing. I already mentioned delta H, and that's kind of obvious. Delta H is how high the water gets sucked up into the glass tube. D is the diameter of the glass tube. And then there's something called the contact angle or the wetting angle. And it depends on what is the tube made out of and what is the liquid. For water that's touching glass, we can assume that that contact angle is 0 degrees. But there are other contact angles, for example, mercury and glass would have a different contact angle. But I think most of the problems we're going to do are going to be for water and glass. And so we'll use a contact angle of 0 in those instances. This equation will tell us what is the force that's pulling that water up. And so we need to think of a force balance here. Something's pulling the water up, and then something is pulling the water down. The surface tension pulls the water up. Why doesn't it just keep going up forever? Why does it reach an equilibrium? Any ideas?
Pressure.
Okay, pressure, what do you mean? Okay. Gravitational force. Right. What we need to remember is that this water has a weight. Let me do it this way. All right. Yeah. Any water that's above this line is heavy. I mean, all of the water is heavy, but this water is going to be wanting to go down because it is above the general water level. And what's pulling it up, the upward force, is this force due to surface tension. And so equilibrium means that the two are in balance. If we put a dry glass tube in water, the water would be sucked up into the glass tube and then it would stop. When it stops, that means it's in a balance. Equilibrium means that the two forces are equal, that eventually the surface tension pulled the water up, but the weight of the water is so heavy that now it's imbalanced with the surface tension. And so the two forces are equal. So let's look at this formula and see what it is saying the surface tension is dependent on. Our previous version of the previous version of the equation said that surface tension was just a length times this sigma. So now this is saying it's pi d. Previously the formula said sigma times L. So why is it saying now pi d here instead of L? It's circular, right. So what is pi d? It's the circumference. So it's the distance around that tube. And so it is where the water is touching the glass. So it's like a length parameter of how long the water and the glass are touching. So it's kind of interesting if you compare the force to the weight of the water. How would we find the weight of the water inside, above this line, above our first liquid surface, from here to there? How would we find the weight of the water in the tube?
First we find the volume.
Volume.
Pi r delta h.
Volume, and then what?
That's we already have the
Multiply by the density, right?
We know the density of the water.
Right. And so you were starting to give me the formula for the volume. What's the formula for the volume?
D over 2 pi delta h.
Okay, so you're thinking about it in terms of the radius, like d over 2, right? Because it's the cross-sectional area times the height. Times the height. So normally in fluid mechanics and hydraulic engineering, we're going, since d is a typical parameter rather than radius, you won't hardly ever be seeing radius anymore. You'll usually be seeing d. We're going to think of the cross-sectional area as pi d squared over 4. That's the area. Okay, so that gives us the top surface area, and then we're going to multiply that by delta H. So this is giving us the volume, and then the density, it's whatever the density of the liquid is. And here, we're going to be doing problems with water. And so we would use, not density, unit weight, right? Unit weight. Because we want weight to be in terms of newtons. So volume is cubic meters, and then unit weight is going to be newtons per meter cubed. All right, so the unit weight is 9810 newtons per meter cubed. All right, so that's how we could find out how heavy is the water that's above the water line. So how can we find delta H? That's how high the water is rising. Any thoughts about how we can find how high the water goes up above this surface? I think somebody knows. Remember equilibrium? We set the two forces equal to each other. So let's do that for a problem where here's the surface tension of water at room temperature, 0.073 newtons per meter. We've got a glass tube with a diameter of 1.6 millimeters, and the water temperature is 20 Celsius. Now the reason why we're given the 20 Celsius, there's two things that we would get from that. That's where we would get the unit weight of the water at 20 Celsius, and also the surface tension is dependent on temperature. So since it said 20 Celsius, we're actually going to use the specific unit weight at 20 degrees Celsius is 9790 newtons per meter cubed instead of the standard 9810. And then
the unit weight is going to be a given.
What do you mean by a given?
Like in the
In the exam? I would maybe give you a table if it wasn't at 20 Celsius, but if I didn't mention the temperature, if I just said water,
Then
then you should,
9810.
yeah. All right, so the surface tension at 20 degrees Celsius is this one that's given 0.073 newtons per meter. All right, so we want to find out how high the water is going to rise. And I give you the whole key right here. This is what equilibrium means. It means set the surface tension force equal to the weight of the water. All right, I'm going to stop talking and give you a chance to collaborate on finding what is delta H. Solve for delta H. It's a really, I'm trying to encourage you to include the units in your calculations. Another thing I'll encourage as a really good habit is to always do a sketch in your problem. If there's any way you can do like a little drawing to show what's happening, you should try that. Even though maybe you've got terrible drawing skills like I do, like that looks awful, right? But it's better than nothing, and it gives you the point. It gives you the idea that D is the diameter, that W is the weight of the water. We know the direction it's going. You can see the surface tension is up. I don't know why I put a second D there. Delta H. And so, if there's a drawing you can do, even though the book maybe has a nice drawing, put it on the paper, because there's something about doing the drawing that helps you to sort of visualize and, hold the problem in your hand in a way. So you can see me setting up the equilibrium here, saying that the force up is the surface tension, the force down is the weight of the water, and equilibrium means that they're in balance. And so I define how to calculate both of those. The weight of the water is just the volume times the unit weight. And then the surface tension is sigma times the circumference. And since the angle is 0, cosine of the angle is 1. Okay, so here's then the equilibrium, where we set everything equal. And I probably could have canceled a few things out early, but what you can see is that the delta H is 4 times sigma, cosine of the angle is 1, diameter, and the unit weight. All right. Any questions about this example? All right, well, let me ask you a question then. What would happen if we made this tube, if the tube had a smaller diameter? What would happen to delta H?
Increase.
It would what?
Increase.
Increase. Okay, there's 3 options. It can either increase, decrease, or stay the same. Who thinks that if you change the diameter of the tube, delta H will stay the same? Nobody's raising their hand. Who will think that if you make the diameter smaller, delta H is getting smaller? Raise your hand. A few people. Now, those of you who aren't brave enough to vote, at least some people are going out on the limb and vote. Who thinks delta H is going to get bigger if you make the diameter smaller? Wow, a healthy vote for that one. Who wants to explain why does delta H, by the way, that's the right answer. It's a little bit hard to understand, because if the diameter gets smaller, the surface tension force goes down, right? Because we know...
But then?
Oh, you've got an argument at the ready. Let me just give you like the, at first glance kind of argument here. So it was going to be sigma times d times pi, right? So here's what I'm saying. Well, I thought if you make d smaller, then the force that's pulling it up gets smaller. Okay? So now f sub s gets smaller when we make the diameter smaller. But you realize what?
Because when you put equilibrium, you're going to divide by the force to find delta H. You divide by a smaller number.
Okay, that's one way of putting it. What do you think?
The weight would be smaller.
The weight would be smaller also. So it's true. We make d smaller. The surface tension force goes down a little, but the weight goes down a lot.
D squared.
Right, because it's d squared, right? Because if we go to the formula here, it was pi d squared divided by 4. This was the area. And then the delta H gives us the height. So here's what's happening. If you make the tube smaller, it's true that the surface tension goes down a little because d went down. So there's a linear relationship. If you make the diameter 20% less, then it makes the force 20% less. But if you make the diameter 20% less, it's going to bring the weight down more than 20% because it's d squared. So any reduction is amplified. So if you make a small tube like, now this one, what was the diameter of this one? 1.6 millimeters. So if we had a tube that was a diameter of 0.5 millimeters, can anybody calculate really quickly how high would it rise in that case? Like when we did all of the canceling out here at the end, let's just do a quick substitution with a new diameter. With a diameter of 0.5, that would give us 4 times the sigma, 0.073 newtons per meter. And then cosine of 0 staying the same. Now we have the diameter here would be 0.5 times 10 to the minus 3 meters. And then our unit weight stays the same, 9790 newtons per meter cubed. So who has a calculator and can do this delta H real quick? How much? 59 millimeters?
Yes.
Wow, 59 millimeters. So the other one was 18 millimeters. So it rises a lot higher. All right, so does everybody understand why? Even though the force gets lower, it rises higher? Yeah. Comment?
What if the tube was so short with like off?
Okay, good question. The water can only rise as high as the tube is. So if the tube isn't adequately high enough, like if this is how high the tube is, it can just go up to the top. The top of the tube is all it can do. It's not like it's going to turn into a pump. It will just go to the top and then stop. Because remember, what it's trying to do, its whole objective is to maximize contact with the glass. So that's why it won't go any higher than where the glass is because all along it was just trying to touch the glass. So that's why it won't go beyond it. Yeah.
So increasing the diameter, the weight of the water will not affect once as it goes up.
What we're saying is that,
So the weight should pull it down.
yeah, you're right. The weight will be pulling it down. This one where it was 59, let's do a drawing of that one. So here is the one where it was going 59. It's going really high. And by the way, it doesn't matter how low into the water it goes, so I don't need to draw it like that. So here's our 59 millimeters. So what we're saying on that one is that the weight of the water is pulling it down, but the surface tension is pulling it up. When we made the diameter smaller, the surface tension was staying high longer than the weight was. So, go ahead.
So the surface tension in this case is greater than
They're equal. If the surface tension was greater, then the water would still be rising. So if we could somehow change the diameter, like if we could make it smaller and smaller and smaller, we would actually see with our eye the water level coming up, but then it would eventually stop when it's in balance. We're out of time. It's 8:50. So remember, you've got a new homework assignment you're working on for next week. That homework assignment is on the course schedule I've given you, and now it's here in the recorded lecture. So have a great day. I'll see you on Tuesday.